Nice job. Okay, so before I introduce our next speaker, we should have a couple minutes at the end for questions, and so we'll probably go through the next couple of talks, and then we'll do a couple questions at the end. Our next speaker is Pankaj Berde of the Open Network Lab. He is a lead architect for the Open Network Operating System. The goal of the Open Networking Operating System is to build an open source distributed network operating system for service provider networks with performance scale. Whoops, you were done early. Performance scale, high availability, and core features that large vendor provider and research community networks could use. Pankaj has been with the ONS project and with the ON Lab since 2012. Before that, he has 20 years of experience in building scalable distributed systems and software products, including databases, storage software, systems management, and big data analytics systems. Pankaj has been involved in building scalable control plane software for SDN for more than 3 years, which, as you know, is a long time in the SDN world. So please welcome Pankaj.
Hello, everybody. Thanks for the nice introduction. Today, I'm going to talk about Open Network Operating System. Some of you may have already heard about ONOS, and the first introduction for ONOS was when we did a mind-blowing demo last year at ONS over here. Today, I want to walk through the journey from last year's ONS to this year, and we have done some exciting improvements. I want to share that with you. Looks like it's back. So ONOS is distributed network operating system for large-scale networks. ONOS is built with scale-out, high availability, and high performance in mind. Last year after the demo, we have been asked this question at ON Lab several times, why, how, and results. And I'll try to address some of these questions during this talk. Service provider networks are a great example of large networks. Each of this network has some characteristics like based on its size based on number of routers, ports, users, or number of applications. They have one more common characteristic. Each of them require high throughput and low latency network operations. Imagine if each of this network would have been an SDN network and it needed a network operating system to manage it. How would that network operating system look like? What would be the requirements for that? So we did some requirement analysis, especially for a core backbone network of a service provider. The primary role of ONOS or any network operating system is to present a global network view or a state and make it available for the applications at one location. We did a sizing exercise of this network state based on one use case, which was traffic engineering on the core backbone. And we quickly found the size of this network for the state could go beyond 200 gigabyte. And as we know, more and more applications are built, more use cases are built. The size is going to grow furthermore. And combine that with low latency network operations. So these are the operations, or these are the event processing, which has to be done in a very low latency. So network events like link going down, port going down, have to be registered into this global network state and made available to the applications. One or multiple applications may react to this network state and update the network state to reprogram the network, and ONOS will propagate that onto the network. We believe this requirement, there's a requirement that this has to this has to be done in a very low latency in a range of 10 to 100 microseconds. So combining these two together, it's a challenge in itself. And we have a high throughput application operations requirement. A most common application operation is setting up paths or modification of path. Applications like traffic optimization can generate 500K to 1 million path operations or network application operations at a time. This is large number of operations, and they are higher level operations. They translate down to somewhere around 3 to 6 million network state updates per second. So in combination of all this requirement, these are tough challenges. And we believe we need a distributed network operating system, which is running in a co-located servers, few servers together to solve this kind of performance problems. So we decided to build one. So the key takeaway is large networks require distributed network OS, which can have scale out, high performance, and high availability. I want to point out that your distributed does not mean geographically distributed, but a single cluster of few co-located physical servers. So can one build a distributed network OS putting together some open source blocks? Yes, and we did it. Last year at ONS, we actually did a very good demo of this. But I'll come back to the but. So how can one build a simple distributed network OS with a simple scale out? A common strategy for distributed systems is to divide your work into multiple parts and get things done independently. So we can divide our data plane into multiple parts and associate multiple instances to manage these data planes. And these instances can work together to build a logically centralized one single controller. And that will need some interconnections so that they can communicate with each other. And together they can build a logical global network view for applications to work off and annotate that. And applications may also be on different instances which will need interconnection, use the same interconnections. So this is a simple distributed network OS, more of a reference architecture for distributed network OS. So last year, beginning of last year, we actually started building on the same lines, building together a distributed network OS using open source components. We divided our network in parts and associated multiple open flow managers to manage these parts of the network. This gives us a simple scale out architecture. As your capacity grows, if you need more control plane capacity, we can add more instances. And these instances have to coordinate with each other. So we built a coordinator using distributed registry, and we use Zookeeper, the open source component, to build that. And all these multiple instances need to work in tandem to create a network graph for an applications to work on top. So we built a network graph abstraction using, again, open source tools like Titan GraphDB and Cassandra. And we presented that to the applications with the standard Blueprints API, which is more of a graphs language API. So applications could use the graph, annotate the graph, and OpenFlow managers could pick up those annotates and program the network. So we demonstrated this at ONS last year, and it was well received. So we could put together a simple prototype or proof of concept in 3 to 4 months using open source building blocks. So we did it. And it was good for rapid prototyping, but it was nowhere close to our performance requirements, which we talked earlier. And more than that, there was hardly any visibility under the hoods of these systems. So why was it so hard to get performance out of this off-the-shelf open source software? Some of the softwares are bloated. They have been customized for various different use cases, and they may not fit for network operating systems. It's very hard to get visibility under the hood, especially the performance visibility. And they are difficult to tweak for customization. And there are some other standard ideas for scalability, and there are some challenges around it. There is one standard idea that we can partition data and processing so each instance can run independently. But there's a challenge here. What is the optimal way to do it specifically for a network operating system? How can we get that performance satisfied? Another standard idea is to replicate data to eliminate remote memory access. Now, the challenge here is to keep these replicas consistent when network state changes. One more standard idea is to make processing stateless, to make failure recovery easy. If there is an instance failure, it can be taken over by some other instances. The challenge here is how to make the state durable across failures, and where do we persist it? So there are lots of challenges to build a network operating system. So the key takeaway is large networks do require a distributed network operating system, and building a distributed network operating system that can scale, have the high performance, and have the fault tolerance poses many hard problems. It's not easy to build one. So that led us to an exciting journey from last ONS till today to build a robust, high-performance foundation, a key SDN building block for building SDNs on top of a network operating system which can scale, which can have the high performance, and which can have the fault tolerance. We learned a lot during this process, and we did some improvements, and we were completely performance focused. So some of the we swapped out some of the heavyweight open source building blocks and replaced it with a lightweight building block called RAM Cloud, which is ultra low latency distributed data store. And we built our custom ONOS graph abstraction on top of that, and we built an in-memory network graph, and we presented it to the controller applications with a simplified ONOS-specific graph API. And we added an event notification framework. So together, we transformed from what was a completely open source building block to a more optimized, more performance-focused building block. And this is how it is today. We have about 100x better performance. One of the interesting things which we found out when we moved in this model is that we started seeing visibility under the hood of these open source products. We quickly found that we had a performance bottleneck where we were doing too many read writes, and there were too many indirections. And it was due to we had built a network, ONOS-specific network graph, which was a very simple network graph on a very generic graph model. And this generic graph abstraction was built on the generic key value store representation. So that caused several levels of index searches and contentions in writing to this, and slowed down the performance. Then we realized our data model is not very complex. It's very simple. We just built it directly on top of ONOS, directly on top of RAM Cloud, and create a network graph on top of it. And that reduced our read-write operations further, and that gave us a lot of, together with RAM Cloud and our own custom pieces, we are seeing about 100x performance boost. So how did we solve these hard problems? And there are still more to solve. So the key, we use lightweight open source components, which we can tweak, and something like RAM Cloud. We use partitioning based on switches to exploit the locality of the data. We cache and replicated some state, and we applied the state machine replication for sequential consistency. And we use kernel bypass for low latency remote communication. Anytime we talk about performance measurements are a key part of it. We cannot do performance improvement without measurements. And what we've learned is that we need, based on our performance goals, which we set based on these requirements, we had to come up with some metrics. And we started measuring the basic network state update latencies. These are like update latencies for discovery of network, like switch ports and links. We measured the latencies for network event processing, something like rerouting of paths in response to link failures. And we also measured the throughput for application path setup. There's an important point to note here that this cannot be compared directly with microbenchmarks like cbench. In fact, we found this metrics to be more relevant to what performance goals we had set and what the performance demands are for a large network. So we started measuring ourselves across this performance metrics, and let's see how our results are. So here the April 2013 results has a lot of variance, and we don't have reliable results for that. The reason for that was most of our instances were VM-based at that time, and we didn't have a good framework. But we know the performance was horrible at that time. It was very bad. It was visibly bad. We moved from there. We built performance benchmarks, and I'm not going to go into details of each of this. The key point here is from hundreds of milliseconds, we are now down under 100 microseconds. And that's a big deal. Getting these operations under 100 microseconds is very important because these are in the critical path of any network operation network OS does. And we have a performance-focused demo today at the show, at the exhibit, and you should actually look at it, and there will be more details. So I'm not going to explain how we did transform these numbers. The next measurements we had is network event processing latencies. Here we are measuring, we have a continuous sampling of measurements by recreating link failure events, and we are rerouting thousands of routes. Here we can see the green is showing the ONOS processing latency, and the blue line is the addition with flow mods or pushing those onto the network. Here latencies are at most important because anytime there is a link failure or a port failure, the network operating system has to react in a very low latency manner. And again, this is at our demo booth, and you should have, this is live in action, and we have performance experts who can answer some of your questions. Another important measurement we did is application path setup latency and throughput. Again, the green shows the ONOS processing time, and this is the continuous sampling. I would like to bring up a point at this point is it's very important for any building block, to provide visibility under the hood. And if ONOS is going to be your SDN building block, we are committed to provide this kind of performance visibility in ONOS under the hood right from the beginning. And that is what we have built it. And we started measuring this performance based on what a large network's performance goals are and how to measure that. And we believe more and more SDN building blocks should adopt this kind of policy to provide more visibility under hood and make it easy for builders of networks to build very efficient systems and have good visibility on their systems. So let me recap our journey so far. We started in October 2012. We had a rapid proof of concept using open source components. We demonstrated some of the key functionalities, and we did an exciting demo at ONS, and the demo was well received. Since then, we worked hard towards December 2013 to build a limited release. We added some functionality, and we improved based on industry standard tool chains for continuous integration and QA, and getting ready for open source processes. We built a development VM for application developers as well as core developers to onboard onto the project. And we have been continuously improving the performance. And today, we are more performance focused, and we are at a point where we can say with confidence that we have a good performance platform. And that is based on by replacing some of the open source components with custom built components and using lightweight components. And we revise our semantics for the northbound abstractions and APIs to make it easier for the applications. And today we have about 100x better performance. With this, my third takeaway for you is that, yes, I'm very confident that ONOS is on track to deliver a stable platform or a foundation to build for a stable SDN, and we are going to deliver a distributed network OS with scale out and high availability and high performance. And we would make it available for you to build your SDN using ONOS. But before we make it available, we want to build some use cases, especially with our partners in the service provider sectors, and validate that this platform is really stable and very robust for you to use. And with that, I'm glad to make this share this information that ON Lab is committed to do an open source release with several use cases by the end of this year. And I can say that with confidence because we have a great team behind it. This is the team which has been working hard for more than a year, building day and night, working hard, the performance metrics, measurements after measurements, slight improvements after improvements, and we are seeing the results of those. And we are hiring, we are looking for more talented people, more talented like this, who can all, and you'll see the smiley faces all around this conference, and you can ask them more questions and ask them. Everybody is intellectually talented to tell you a lot about their learnings, and everybody has something to tell you about how to build a scalable SDN platform. We have some exciting demos at ONS 2014. We have a showcase demo with ONOS running live on a real wide area network, an Internet 2 SDN network. And we have another performance-focused demo at ONLab booth, where we have our latest performance results and benchmarks. And we have experts to give you all the insights about what an SDN platform should provide and how to look under the hood of an open source component and learn from it. Thanks.